Hi, I'm Gil, a junior at Brown University, and the work I am presenting here has been done while I was an undergraduate researcher at the Artificial Intelligence Lab and was accepted to the American Medical Informatics Association Summit this year. The paper is titled Diagnosis, Prevalence versus Efficacy in Machine Learning-Based Diagnostic Decision Support. So currently there's a problem with doctors misdiagnosing patients. Singh from Baylor College of Medicine found that 1 in 20 adults may be diagnosed every year. And there are further studies supporting this theory, and therefore there's been a focus on how technology can help doctors decrease diagnostic errors by accurately predicting patient diagnoses from a list of symptoms. Liang of the Guangzhou University of Medicine 2019 found an F1 score, which is a measure of accuracy mixing both precision and recall, of 0.885 across 13 most common diseases. A perfect F1 score is 1, so this is quite high. Baumel in 2018 found an F1 score of 55.86% for the 20 most common diseases. However, there's a disparity between these studies and the real world, since doctors do not just diagnose the most common diseases that we have the most data for. They must consider all possible diseases. Therefore, the study aims to address this disparity and evaluate machine learning classifiers on growing data sets of increasingly infrequent diagnoses, so we can get a realistic account of how good our machine learning classifiers are in supporting doctors' decisions. To do this, we use the Medical Information Mart for Intensive Care 3, or better known as the MIMIC3 dataset, which holds data for about 61,532 intensive care unit stays and the Beth Israel Deaconess Medical Center in Boston, Massachusetts over the course of 11 years. To assess what the patient's primary diagnosis was, we use the ICD-9-CM code, which is assigned by doctors for billing purposes, but are given a priority ranking. If their priority is 1, this is assumed to be the primary diagnosis of the patient. So by using SQL queries, we found the 50 most common up to 1,000 most common ICD-9-CM codes to build our data set of patients. To find the top 50 ICD-9-CM codes had 27,615 admissions, while the top 1,000 ICD-9-CM codes had around 51,000 admissions. To decide what features we wanted to include for each patient, we broke up different features into 4 categories. First is the comorbidity or the other ICD-9-CM codes the patient was diagnosed with that was not priority ranked 1. Second was demographical data such as age, gender, and marital status. We removed patients that were under the age of 18. The third and fourth categories are lab results and chart events, which is data collected by the hospital or any tests run by a hospital during the ICU stay. We only use lab results and chart events that were done for 60% of the patients, and if any data was missing from the patient, we imputed the population mean for that respective attribute. This completed our data set, and then we were ready to move on to our next experiment with all of our admissions and the 51 features that we collected to our 2 experiments. The first was model comparison. Using the top 50 dataset just for efficiency and speed purposes, we ran that dataset with 44 different classifiers and different hyperparameters. We considered logistic regression, support vector classifiers, and use support vector classifiers, nearest neighbor decision trees, random forest, multi-layer perceptrons, and neural networks. With the different hyperparameters, this totaled to 44 different classifiers, and we found that the best classifier was the multi-layer perceptron. Using that classifier, we then took the data sets with increasingly rare diseases and ran it on that classifier to see how accurate that classifier was when the diseases got more rare. The second experiment we ran was a feature importance experiment. We individually moved each of the 51 features of the top 50 ICD-9 code and saw the effect of removing that feature with the multi-layer perceptron classifier, the best performing classifier. By doing this, we could see which features were most important for the data to help the classifier become more accurate. So first, let's go over our key findings of the model comparison study. We found that the multi-layer perceptron was the best classifier, and with the different hyperparameters actually constitute the top 3 best classifiers, with the top score being 0.282 on the top 50 ICD-9 codes dataset. The next best classifier was the random forest classifier with the highest score of 0.279. Now we ran that classifier on the different diseases. So these are the top, on this graph, each data point represents a different disease, and these are the top 50 diseases, just to be able to actually see the data. We tracked how many number of admissions were in the training data set. This is on the x-axis, and then we tracked the average F1 score of that disease, and this is on the y-axis. So we see quite a correlation between the number of admissions and the average F1 score. The blue dots represent the data from the multi-layer perceptron classifier, and the orange dots represent the data from the random forest classifier. To quantify the data further, we ran these classifiers with a Pearson correlation coefficient to quantify the relationship between the number of diseases examined and how many admissions that disease had, and the F1 score, how accurate we are to predict that disease. So we can see that from this table, you can see that we range from a moderately strong correlation now of 0.56 all the way to a strong correlation of 0.7. So we see there is a positive correlation between the number of admissions and average F1 score. The second thing to note on this table is how quickly the F1 score drops when the number of diseases examined increase. So for the top 50 diseases, we had an average F1 score of 0.28, and that drops to 0.09 when we add 150 more diseases or have a data set of 200 diseases. And then it doesn't get much better as we start decreasing. Another thing to note is that the correlation coefficient becomes stronger when diseases become more rare. This is noticed in both the MLP and random forest. So we can see that relationship of how many data points you have in the training data set becomes even stronger when you have examples with very few data points. The second experiment that we ran was feature importance. So we took each feature that we individually removed and broke them up into categories. So we found that the lab events were the most important features, and they had an average change of F1 score of 0.11. So they really impacted the data set. The second most important category of features to have was comorbidity of ICD-9 codes, and that had a change in F1 score of 0.07. To discuss a little bit further more our findings, we found that the best F1 score was 0.282. This is quite lower than the studies found previously with just the top 20 diseases. It also is not effective enough to accurately trust and support doctors currently. It is also important to note that the F1 score of the 6 least common ICD-9 codes was 0. So the classifier could not accurately classify any examples of that disease. It's also interesting to note that the 5 most frequent lab events were negligible in classifier performance. So common tests that we think should provide a plethora of data actually were not quite important to the classifiers that we ran. And additionally, the top 6 ICD-9 CM codes had an F1 score of 0.5 or higher. So we are only seeing that the top 6 diseases do a better than average job of guessing and predicting the diagnosis of patients. Throughout the study, we do use ICD-9 codes to assume patient diagnosis. We also ran all the classifiers and tests using the Python scikit-learn library. And that's also how we calculated all the correlation coefficients, as well as using the Python scikit-learn library. The next steps would be for future research into maybe organizing groups of diagnoses into categories. So classifiers, instead of having to predict a specific diagnosis, just have to predict a category, and that can also assist doctors in diagnosing patients more accurately. We also suggest applying more advanced techniques with large data sets to see if that helps the improvement at all. Thank you for listening and taking time out of your day to listen to my research. If you are interested in seeing the paper or learning more about my research or other research from this lab, please visit our website.